everyone, welcome back to this third video of the same chapter, the role of chemical and physical properties in engineering materials. So we will focus on physical properties. They can be measured without destroying or changing the material, and we have some sub-properties like thermal, magnetic, gravimetric, electrical, optical, and acoustic. For the thermal, we have melting point, specific heat, thermal conductivity, thermal expansion, and heat restoration. For the specific heat is all about the amount of heat energy required to raise a given mass of material. 1 gram at a given temperature change, or BTU per 1 billion Fahrenheit in the English system. So this property is very important because it determines the cost. For the specific heat, I just did a problem for you. Just find the amount of heat required to raise a furnace load of steel parts from room temperature to 1800 Fahrenheit, and this is the answer. It's normally just applying the equation as it is, and this is another example. So let's move on to the thermal expansion. It's important when dissimilar materials will be fastened and heated, and also when materials are locally heated. The units are they. So if you heat a definite shaped material, does the hole in the center get bigger or smaller? What do you think? So when a solid is heated, there is an increase in the linear dimensions as the temperature rises. So we have here the length, the area, and the volume. And these are some equations. So to explain this behavior, it's necessary to examine the nature of the bonding between atoms within the solid. I did a thermal expansion exercise as well. Here is the solution for it. You can just practice it alone. So for the thermal conductivity, we have 3 elements: metal, ceramics, and polymers. So for the metals, relatively large numbers of free electrons are available for heat transport via collisions, and impurity atoms lead to an increased chance of scattering of the mobile electrons, leading to a decrease in thermal conductivity. For ceramics, the thermal conductivity is low since very small numbers of free electrons, and the thermal conduction by phonons only. So the transmission of thermal energy by phonons is not very efficient, and lower thermal conductivities for amorphous ceramics due to increase in phonon scattering. For polymers, we have the thermal conduction by phonons only, and it's significantly reduced by presences of pores from foaming during manufacture. So it is the steady state heat that will be transmitted by a material of given thickness and temperature differential per unit area. These are the units. So we have the Q, this is the equation of thermal conductivity. So Q is the heat flow through material per unit time, the K is the thermal conductivity, A is the area through which heat will flow, and delta T is the T hot minus the T cold, and it's the temperature differential. So it's the use of thermal conductivity to compare window heat losses. There is an exercise here that you can just apply the equation straightforward and you find the solution. We have also the heat distillation temperature of some common plastics. Now let's move on to the electrical properties. So the electrical conductivity is simply the reciprocal of the electrical conductivity, and it's also the electrical resistivity is Rho equal AR over L. So the A is obviously the cross section of the wire, the R is the resistance in ohms, and the L is the length of the wire over which the measurement is made, and the conductivity is 1 over O. For the magnetic properties, we have at least 20 magnetic properties that are cited in the AMST handbooks. And the magnetic property the most used by a material designer is ferromagnetism. And only 5 of the stable elements have this property, namely iron, nickel, cobalt, gadolinium, and dysprosium. Also, many oxides and ceramics can be ferromagnetic. So, the spin of an electron combined with its electric charge results in a magnetic dipole moment and creates a small magnetic field. And also, when these tiny magnetic dipoles are aligned in the same direction, the individual magnetic fields add together to create a measurable macroscopic field, and it's called ferromagnetism. This is the variation of the magnetic strand H versus the flux density B. So this is an example of a soft magnetic material and another example of a hard magnetic material with good permanent magnet. This is gravimetric, so this is the density and specific gravity, and it's also the ratio of density of a substance to a density of a reference substance. So it's all about comparing costs of various materials and determining the porosity of materials. This is a problem of gravimetric. You can look at it, and here is the solution. So for the optics, we have the refractive index. So it's a light in vacuum and light in materials. We have color. So for example, titanium nitride coating applied to the polished door. We have the elastic modulus and the modulus of elasticity. It reflects the degree of elasticity of a given material. And here is the Hooke's law. It's very, very important. So the modulus of elasticity is obviously the stress over the strain. Stress over the strain. And the measurement of the elastic modulus E is by measuring the velocity of sound in a material. So it's the modulus of elasticity over the density. And by the way, the elastic modulus is considered as a physical property because it's a principal property of the material, and it does not change with heat treatment, manufacturing techniques, and shape. And the elastic modulus changes with the temperature. The steel elastic modulus is relatively unchanged up to a temperature of about 426 Celsius. So the effect of the elastic modulus on the deflection of cantilever beam from different materials. These are just examples of deflection of 1 inch, 3 inch, and 60 inches. So how is this property is used? Simply, a spring constant is used to calculate the force required for a given spring deflection, and the elastic modulus is the spring constant for elastic solids. So the material retains its elasticity as long the material is not deflected to the point where it cannot recover. And here is an example. So a cafeteria bridge with unsupported span of about 60 foot wide by 140 foot long. So the strain of the main girders is continually monitored as the structure was put to use and as it aged. And when the wires stretched by the structure deflection, the diameter change is sensed electrically and recorded. Now we will see the Poisson's ratio. So it's the ratio of lateral contraction to longitudinal extension, and it is the Poisson's ratio for most metals is about 0.3. So if a bar is pulled actually in the elastic regions, the bar will get longer and the diameter will get smaller. So the ratio of the two strains lateral axial is called the Poisson's ratio. So the modulus of elasticity on shear, when the material is not loaded axially but in shear, its modulus of elasticity on shear is related to the elastic modulus.